alpha beta pruning can also be considered as advanced min-max algorithm because in case of min-max algorithm the complexity of the algorithm is order of b raised to d, where b is the branching factor and d is the depth. So what is branching factor? Suppose in this tree you can see all nodes have two children, fixed two children, so that's why the branching factor is 2. And what is the depth? Suppose this is 1 2 3 4 5, so this number of levels are called depth. So min-max algorithm, the complexity is this one, but in case of alpha beta pruning the complexity for the average case or best case is order of b d by 2. So you can see the complexity for alpha beta pruning is much better than min-max algorithm. So let us start the process of alpha beta pruning, and here I would like to discuss one thing. What is pruning? Pruning means the cutoff. Okay, so here in min-max algorithm we explore all the possible paths, but in case of alpha beta pruning we cut off some of the less promising paths. That's why you can see the complexity is much better than min-max algorithm, because we are not going to work unnecessary, okay, or we are not going to explore all less promising paths. Okay, so let us start our process. Suppose in this tree, as you can see, the top level is max, and alternative we can write max min, then max, then min. So you know in min-max algorithm root is considered as max, and after that we write minimum, then maximum, then minimum. Alternatively we have to write these things: max min, max min. And what is this alpha and beta? Here max node is referred as alpha, and min node is referred as beta. And theoretically we assume that initial value of alpha is minus infinity and the initial value of beta is plus infinity. Okay, so let us start our process. So these are the terminals. You can see 4 3 4 5 9 5. These are the terminals, and this is the minimum level. And we know that alpha beta pruning is a special type of min-max algorithm, and min-max algorithm is based on depth first search. So here we are going to apply depth first search, okay, in the given example in this tree. So let us start. This is 4 and this is 3, and since it is a min level, so we need to write here beta, and the value of beta is 4 and 3. Which one is lesser? 3 is lesser, so value of beta is 3 over here. Okay, when we got the value of beta, we need to propagate this value according to the depth first search procedure. So this beta equals to 3, okay, gives alpha equals to 3. Why do we write alpha over here? Because this is a max level, so here alpha is used. alpha is attached with the maximum and beta is attached with the minimum. Now alpha equals to 3, and according to the depth first search we have to find out the value of this child also. So let us find out. The value of I is 4 and 5, and this level is minimum level. So here the value of I node is beta equals to 4. Okay, are we getting this? Now here beta equals to 4 and beta equals to 3, and D is present in the max level. So here you need to change the value of alpha from 3 to 4. Okay, because this alpha always takes the maximum value available in the children. So here 4 is the greater value, so we need to change the previous value of alpha from 3 to 4. Now let us proceed with the process. So here alpha equals to 4. Now this is a minimum level, so here beta equals to 4. Now beta becomes 4. Okay, we have to copy the value of the child node to the parent node. Since it is a minimum level, so here we need to write beta. So this 4 is copied from alpha to beta. Here beta equals to 4. Now let us find out the right child of this node B. So here right child is E. We need to follow the depth first search procedure. So next we need to find the value of J, and since it is a minimum level, so we need to write beta equals to, which one is minimum? This 5 is minimum. Okay, now this 5 is propagated to this upper level, and the value of alpha at node E becomes 5. Okay, becomes 5. So as soon as you get the value of alpha equals to 5, okay, and you can see the other child have alpha equals to 4, and since it is a min level, and at node B you can see beta equals to 4. So it is clear that at this minimum level you are going to take the minimum available value, and here you can see the value alpha equals to 5 is greater than this value alpha equals to 4. So this B node is not going to consider this particular direction, okay, or this particular part of the tree, because here already you got a value which is greater than this value 4. Okay, so that's why the alpha beta pruning method is not going to explore this part of the tree. Okay, or in other word you can say that the whole part or whole sub part of this tree is going to be pruned. Okay, so this way you can save the searching, and that's why you can see the complexity of this alpha beta pruning is better than this min max procedure. Okay, so this particular part is not going to be explored. Now let us proceed with the procedure. Here beta equals to 4, and since it is a maximum level, so you need to write, or you need to propagate this value at node A. So here alpha equals to 4, alpha becomes 4. Now follow the depth first search procedure, find out the values for this child of node A. So let us find out. Yes, so first you need to find the value of this L node, and since it is a minimum level, so you need to write beta equals to 1. Okay, and when you write beta equals to 1, this value should be propagated to the node F, and here alpha becomes 1. Okay, now let us find out the value for this M node. So since it is a minimum node, so you need to write beta equals to 3. Since and when you write beta equals to 3, the value of this alpha should be changed. So you need to write alpha equals to 3. Why? Because 1 and 3, which is the greater value, 3 is the greater value, or you can see F is present in the maximum level, so that's why you need to take maximum value out of the available values. When alpha equals to 3, you can write here beta equals to 3. Okay, when you write beta equals to 3 and the upper level is, or we can say this node A is present in the maximum level, and A already got its maximum value, which is 4. Okay, so A is not going to consider this path. Why? Because here the value is 3. Okay, and the level is minimum, so all feature values those belong to this node C would be equal to 3 or less than 3. So there is no case when A is going to consider this particular part of the tree. Okay, so that's why you can see this part of the tree is not going to be explored or not going to be taken into consideration, and again you can see you have saved this much amount of efforts or this much amount of searching. So that's why this alpha beta pruning is faster than min-max algorithm, and you can see very clearly with the help of this example. Okay, so that is all about alpha beta pruning. Thank you.